Alright, so here we have a matrix 1 0 1 1 0 minus 1, and we are required to find the SVD or the singular value decomposition, right? So these kind of questions are pretty straightforward and they appear very commonly in a lot of examinations. So you can divide the whole process into three stages, right? The first step is that you find the eigenvalues and eigenvectors of A transpose A, and the eigenvectors will form the columns of Q2. And then you multiply the eigenvectors of A transpose A by A to obtain the eigenvectors of AA transpose. Now this will form the columns of Q1, and sigma will be nothing but the under root of the eigenvalues of A transpose A. Now the question arises, why do we start with A transpose A and not with AA transpose, right? So why A transpose A and not AA transpose? The reason being, so this A is a 2 by 3 matrix, right? 2 rows and 3 columns. So A transpose A will be 3 by 3 and AA transpose will be 2 by 2. So we will always look at the larger one so that we get all the eigenvalues, although there will be some zeros, right? Now let's get started. So what will be A transpose A? So this will be 1 1 0 0 1 minus 1 multiplied with 1 1 0 0 1 minus 1. This will give us 2 0 0 0 0 0 and 0 0 2. So this is A transpose A. Now to find the eigenvalues, what do we have to do? We have to find the characteristic equation of A transpose A, which is nothing but the determinant of A transpose A minus lambda I setting to 0, right? Now this will be nothing but 2 minus lambda whole square times minus lambda equal to 0, which means lambda is 0 and 2, right? And 2 has algebraic multiplicity 2, which means 2 is repeated twice, right? So this is the characteristic equation. So we got the eigenvalues, right? Now we have to find the eigenvectors corresponding to each of the eigenvalue. Let's start with lambda equal to 0. So to find, so what does this mean? What does this mean that lambda equal to 0 is an eigenvalue? It means that A transpose A when multiplied with some vector V is equal to lambda into V, right? Where lambda is 0 and V has to be a non-zero vector, right? V is the eigenvector. We have to find V, okay? So I can write this as A transpose A minus lambda times the identity matrix multiplied with V equal to 0. Now this gives us 0 0 0 again by putting lambda equal to 2, 0 minus 2 0 and then 0 0 0. This multiplied with, so let me write V to be V1, V2 and V3. This will give us 0 0 0. Now from here I can conclude that V1 can be anything, V3 can be anything, but minus 2 times V2 should be 0, which means V2 should be 0. So this is the only criteria that we have, right? That the second component of the eigenvector should be 0. So what is the eigenspace? So the eigenspace corresponding to lambda equal to 0. So by eigenspace, I mean the space spanned by the eigenvectors, right? So all elements of the eigenspace will be eigenvectors, right? So this can be written as the first component can be anything. So let me write T. The second one has to be 0 because V2 is 0. And the third one can be anything. Let me write S. So this can be written such that T and S are real numbers. Now I can alternatively write this as T times 1 0 0 plus S times 0 0 1, where T and S are real numbers. Now notice that these two form the basis of this. So you can write this as span of 1 0 0 and 0 0 1, right? So these are the eigenvectors and this will go into the columns of Q2, right? So another confusion that most people have is that why is it Q2 and not Q1, right? So people often get confused with A transpose A, right? And this corresponds to Q2 and this corresponds to Q1. People often get confused. So one way to remove it is that now if I write A to be Q1 sigma Q2 transpose, that means A transpose A will be Q2 sigma transpose sigma times Q2 transpose, right? Now this means that these are the sigma transpose sigma actually contains the eigenvalues. It's a diagonal matrix containing the eigenvalues of A transpose A, and Q2 contain the eigenvectors of A transpose A. Similarly, A transpose can be written as Q1 sigma transpose Q1 transpose. So Q1 corresponds to eigenvectors of A transpose. This is actually the standard diagonalization of which is available for any symmetric matrix. Now let's continue with the problem. Now we have to find eigenvectors corresponding to the next eigenvalue, which is lambda is equal to 2. So again, we will do A transpose A minus 2 times identity matrix multiplied by V should be equal to 0. We have to find V. This will be equal to 2 0 0 0 0 0 and 0 0 2. Right? So there's been a small mistake. The first calculation corresponds to lambda equal to 2, right? And this corresponds to lambda equal to 0. Multiplied by V1, V2, V3 will be equal to 0 0 0, right? Let me correct this here, lambda equal to 2. Now I can say that for lambda equal to 0, we have the condition that 2 times V1 should be 0 and 2 times V3 should be 0, which means V1 and V3 should be 0. So what will be the eigenspace corresponding to lambda equal to 0? It will be nothing but the first component has to be 0, the second component can be anything, let me write t, the third component should be 0, right? So this is actually a one-dimensional subspace, right? And this is the span of 0 1 0. So this will be the third column. So this is the first column of Q2. Let me write it as Q21. This is the second column, Q22, and this is the third column, Q23. Okay. So what is Q2? So now we obtain Q2 to be equal to 1 0 0 0 0 1 and 0 1 0. So the first two columns correspond to the eigenvalue lambda equal to 2, and the second one corresponds to the eigenvalue lambda equal to 0. Also, we write the columns in descending order of the eigenvalues, right? So we write it in descending order of eigenvalues. Okay. Now let's get to the second part of the problem, second step of the problem. The second step says to multiply the eigenvector of A transpose A by A to obtain the eigenvectors of A transpose. Now let's see why that makes sense. So what we have obtained are eigenvectors of A transpose A, right? What does that mean? That means we have obtained V eigenvectors such that A transpose A multiplied with V is equal to lambda V, right? Now this means if I multiply by A on the left, I can obtain A times A transpose A V is equal to A times lambda V, which is same as saying A transpose multiplied by AV equals to, since lambda is a scalar, I can pull it out and write it this way. Now observe carefully that it means that AA transpose multiplied with some vector, let me call that W, is equal to lambda times some vector W. So this means that lambda is again an eigenvalue of AA transpose with the eigenvector W, right? So this is why we, instead of again going through the eigenvalues of AA transpose, we simply multiply V by A and obtain this, right? So let's do that one by one. So if I multiply A with Q21, this is the first column of Q2, I will get 1 1 0 0 1 minus 1 multiplied with 1 0 0, this will be 1 1. So this is not normalized, so I'll normalize it to obtain 1 by under root 2, 1 by under root 2, right? Now let me multiply the second column with A. This will give me 1 comma minus 1. Again, if I normalize this, I'll get 1 by under root 2 comma minus 1 by under root 2. In fact, we don't have to look at the third column. The reason being Q1 is a 2 by 2 matrix, right? Also, we can ignore eigenvalues 0, because 0 is not an eigenvalue of AA transpose, right? But still, if we compute this also, we will get 1 1 0 0 1 minus 1 multiplied by 0 1 0 will turn out to be 0 0, which means that it has no relevance, right? So this vector will form the first column of Q1, and this will form the first column of Q. This will form the second column of Q1, right? So we can obtain Q1 to be equal to, let me write 1 by under root 2 outside, 1 1 1 minus 1. So this is our Q1. So we've obtained Q2, we've also obtained Q1. Now we are left with obtaining sigma, right? So we know that sigma is nothing but, so from this equation, right? So from this equation, let me write A as Q1 sigma Q2 transpose. I can rewrite this. So when I multiply A by A transpose on the left, I will obtain A transpose A equal to Q2 sigma transpose sigma, right? And then Q2 transpose, right? So let's look at the dimensions one by one. A is of dimension 2 cross 3. Q1 is of dimension 2 cross 2. Sigma is of dimension 2 cross 3. And Q2 transpose is of dimension 3 cross 3, right? So sigma transpose sigma will be of dimension 3 cross 3. And since Q2 and Q2 transpose are the eigenvectors of A transpose A, this is nothing but the diagonalization of A transpose A. Let's see why this is true. If I multiply on the right by Q2 and on the left by Q2 transpose, I will get Q2 transpose A transpose A Q2, sorry, that will be equal to sigma transpose sigma, right? So this will be equal to, so Q2 transpose will be V1, V2, V3, right? Expressed as rows, where what are VIs? VIs are the eigenvectors of A transpose A. This is how we defined, right? Defined Q2 to be. Now, since the first column of Q2 is V1, right? So, and V1 is an eigenvector of A transpose A corresponding to the eigenvalue say lambda 1, then we can write the first column as lambda 1 times v1, the second column as lambda 2 times v2, and the third column as lambda 3 v3, right? Now since vi's are orthonormal, we will have lambda 1, lambda 2 and lambda 3 on the diagonal, and all other elements, non-diagonal elements, will be 0. Because we know that vi transpose vj is equal to 0 if I is not equal to j, and it is equal to 1 if I is equal to j, right? This is the condition for orthonormality of the set vi's, right? Now let's come back to the problem. So that means that sigma transpose sigma will be nothing but under root 2, under root 2 and 0. And the non-diagonal entries will be 0. So obviously since sigma is of shape 2 cross 3, right? This means that sigma will be nothing but under root 2, 0, 0, 0, under root 2, 0. This will be sigma. So we've obtained sigma, right? Before that we obtained q1 and we also obtained q2, right? So to summarize, we start with finding q2 as the eigenvectors of A transpose A, and then we multiply each of the eigenvector by A to obtain the eigenvectors of A transpose. And these eigenvectors of A transpose will form the columns of q1. Sigma is the most straightforward thing. It is nothing but the under root of eigenvalues of A transpose A. One more thing to note is that A transpose A and A transpose both will have the same set of eigenvalues except a few zero eigenvalues. If you require proof of any of these results in detail, feel free to put it down in the comments below. Alright, so here we have a matrix and we have 4 options which we need to check if it's true or false, right? Okay, so let's get started with the first one. The first one asks if A is a unitary matrix, right? So a matrix is said to be unitary. So when is a matrix said to be unitary? A is said to be unitary if A star of A is equal to the identity matrix, right? Now, so it's quite straightforward. A star of A will be nothing but, first let me write A star. Again, star denotes conjugate transpose, which means you take the conjugate, by conjugate I mean the complex conjugate, and then the transpose, right? So A star will be nothing but 1 by under root 2 minus I by under root 2, 1 by under root 2 again, and I by under root 2. This is multiplied by A, which is 1 by under root 2, 1 by under root 2, I by under root 2, minus I by under root 2. So now if you simply multiply the matrices, you'll get half plus half, and then 0, and then 0 again, and then half plus half. So this will give 1, 0, 0, 1, which is the identity matrix of order 2, right? So we can say that yes, A is indeed a unitary matrix. The second option says, let V be any vector, then the norm of AV equal to the norm of V may or may not be true, okay? So firstly, the norm of any vector W, so let W be a vector in Cn, the norm is defined to be nothing but the under root of W star W, right? So this is the definition of norm, right? From this we can say that the norm of AV will be nothing but under root of AV star AV, which is equal to the under root of V star A star and then A times V, right? A times V. Now this is equal to, since A star A is identity, this is nothing but V star V. And this by definition is the norm of V. So this is always true for a unitary matrix, right? So for a unitary matrix, AV norm will always be equal to the norm of V. So this option is actually wrong. Now so the third option says that the eigenvectors are orthogonal, right? Typically, this is a result which says that for all unitary matrices, the eigenvectors will be orthogonal, right? And this follows from spectral theorem. Now, but let's see if W and V are eigenvectors of A corresponding to eigenvalues lambda, say lambda 1 and lambda 2, right? Then what can you say about V star W, right? So V star W, or instead let's look at the term AV star AW, right? This will be equal to V star A star AW. Again, since A star is identity, we can write this as V star W, right? Also, since V corresponds to the eigenvector of eigenvalue lambda 1, we can write this as lambda 1 V star lambda 2 W. That will be equal to, so since lambda 1 and what are lambda 1 and lambda 2? Lambda 1 and lambda 2 are scalars. In fact, they can be from C, right? So when we take conjugate transpose of a complex number, we'll get lambda 1 conjugate times lambda 2. This is a scalar. And then we have V star W, right? So we see that V star W is same as lambda 1 conjugate lambda 2 V star W. So by this we can say that V star W, this is a scalar, multiplied by lambda 1 conjugate lambda 2 minus 1 is equal to 0. So either of them should be 0, right? Now, if lambda 1 conjugate lambda 2 minus 1 is 0, that means if this is equal to 1, that means that lambda 1 conjugate lambda 2 will be equal to lambda 1, right? Because I've multiplied it by lambda 1. Now this means, now lambda 1 times lambda 1 conjugate will always be 1, right? So this means that lambda 2 is equal to lambda 1, right? So what can we conclude? We can conclude that if the eigenvalues are distinct, so if eigenvalues are distinct, then the eigenvectors will be orthogonal, right? This is what we can conclude. So essentially we have that if we show that the eigenvalues of the given matrix A are distinct, then we can conclude that the eigenvectors will be orthogonal. So to compute the eigenvalues, let's look at A minus lambda I, right, equal to 0. This is the characteristic equation. So this gives us lambda minus 1 times lambda plus I minus I equal to 0. This can be written as lambda square plus I minus 1 times lambda minus 2I equal to 0. Again, so whenever there is a degree 2 polynomial, right, the roots will be complex, right, and they will be conjugate of one another, right? In fact, by Sridharacharya method, we can say that the roots are nothing but 1 minus I plus minus under root 3 times 1 plus I divided by 2. Right? And definitely both the roots are not equal. In fact, for them to be equal, we need the criteria that this part should have been 0, but this is not 0, so they are not equal. So since they are distinct, we can say that the eigenvectors are orthogonal. So the third option is correct. Now the fourth option asks if every eigenvalue is of length 1. So now let's say let alpha be an eigenvalue of A. What does that mean? That means AV is nothing but alpha V for some V non-zero, right? Non-zero vector, right? If this is so, in that case, we can write that AV star AV will be equal to V star A times V. Again, A star A will be identity, so this is nothing but V star V. But we can also write this as alpha conjugate alpha multiplied with V star V, right? So combining these two things, we can say that alpha conjugate alpha is equal to 1. Because since V star V is non-zero, because V is non-zero vector, so alpha conjugate alpha is 1. This means that the modulus of alpha is 1, right? So the last option is also correct. So here we have a question. This is about PCA, principal component analysis. So it asks what is the primary goal of PCA, right? The first option says to find the directions that capture the maximum variance in the data. This is true, actually. The second option says to find directions that capture the minimum variance. This is not true because we need the maximum variance in the data. In fact, if suppose the data points are distributed in this fashion, then we take the first principal component to be along this line, right? So this will be PC1 or principal component for 1, right? Because this is the direction along which the data points are spread the most, right? The third option says to increase the dimensionality of the data. This is false because we need to decrease the dimensionality, right? That's why we use PCA, right? And then it says to reduce the number of data points. This is definitely not true because we can never reduce the number of data points that are available to us in the data set, right? So the last three are false. Only the first one is correct. Now, if you want a theoretical proof, a very simplified theoretical proof of why maximizing the variance in the data is same as minimizing the reconstruction error, let me know in the comments down below. Alright, so here we have 3 data points given, and the question says suppose we want to project the above dataset onto a one-dimensional space using PCA, right? Now the first question says compute the sample covariance matrix, and then we are required to find the principal direction that is chosen. And there is also another question which asks for the projection vectors, right? So let's do them one by one. One more thing to note is that typically this process is very complex in the sense it's very computationally intensive. Now you have to start with the covariance matrix, then find its eigenvalues, find each of its eigenvectors which will act as the projection, and then you have to find the projection for each data point, right? So this is a very computation intensive process, but this particular problem we will find that it's geometrically very straightforward, right? And I think this question was designed to test the geometric understanding of PCA, right? Okay, so let's get started. So the sample covariance matrix is given by 1 by n times x minus x bar. So this is x1, right? This is x2 and this is x3, right? So x bar would be, so let me write x bar as, so it would be 1 1 1 1 1 1 1 1 1. So what I have done is I have computed the mean, little x bar, little x bar and little x bar. So all of them are identical, right? And we can say that little x bar is nothing but x1 plus x2 plus x3 by 3, right? So it will give you 1 1 1, right? Now if you make this computation, you will get 1 by 3 times, right? 0 0 0 minus 1 1 minus 1 1 minus 1 1, and then the transpose of that, right? So just to recall, this is the centralized data point, okay? So centralized, I can say x1. Similarly, this is the centralized x2 and this is the centralized x3, right? So this will give me 1 by 3 times 2 minus 2 2 minus 2 2 minus 2 2 minus 2 2, right? Okay, so this is the covariance matrix. Okay, now let's do a quick geometric interpretation of these data points, okay, of the centered data points, right? So let me say this is the z-axis, this is the x-axis, and this is the y-axis, right? So let me write z here, x here, and y here. Now the centralized x1 is actually sitting at the origin, right? What about the centralized x2? It is at a point where x is minus 1, y is 1, and z is minus 1, which means it is somewhere here. And centralized x3 is nothing but the negative of that, right? So it's lying somewhere here. And what is this point? This point is minus 1, 1, minus 1. This point is 1, minus 1, 1. And this is definitely the origin. Now, one thing to be noticed is that we can actually join them on a straight line, okay? And since these three data points are collinear, and so this is the line which crosses through all these points, right? So the principal component 1 will be along this line, right? So it will be along this line, the blue line, okay? But what is the direction of this line? It's nothing but 1 minus 1 1, but again we have to normalize it, so we divide it by under root 3, right? Because under root 3 is the norm of this vector, right? So this is PC1, right? So that is the answer to the second question. Now regarding the third question, what will be the projections? Now since the points are collinear, so let me just write that down. The points are collinear. Collinear means they are lying on a straight line, right? Then the projections are the points itself, right? See, typically what do we do? Typically we find a line and then we project the data point onto the line. But here there's nothing to project, right? The point is already on the line, right? And that is why we say that the projections are the points itself, right? Again, this is a special case, and because this particular data set is designed in a way that it's easy to compute the eigenvector. So this is a question on gradient descent and learning rate, right? So we know that the gradient descent algorithm starts at some point, say x0, and it finds x1 by the following method: x0 minus the gradient of f evaluated at x0 multiplied with some scalar eta, right? Now this eta is called the learning rate. Now definitely when eta is small, so as eta decreases, we can say that the speed of convergence also decreases, right? That's why it's called the learning rate, right? Because the rate at which the algorithm is learning, okay? So eta is directly proportional to the speed of convergence, but at the same time, if eta is very large, if eta is very large, or let me just write eta is large, okay, very large, then what happens is that it crosses the maxima, it crosses the optimal value and lands in a different value which is far away from the optima, okay? Now if you think about a convex function, right, suppose you're starting here, okay, at some point, let me call this x0, and your learning rate is very high, then this might end up in moving to this part, and then it can come here and then maybe go somewhere else, because the learning rate is very high. So it can move in this manner, either towards the optimal value or away from the optimal value, right? So this is the problem of having a very large uh, divergence, a very large learning rate, right? Because the algorithm might diverge. In fact, I have covered some intricacies of why all these things happen in a separate video. Uh, so that video will give you pretty much very good insight onto on why you know these things happen with the learning rate, right? In fact, it explains the whole algorithm by looking at an inequality, right? So we can say that, coming back to the question, we can say that a small learning rate can lead to slow convergence. So this is a true statement. A large learning rate can cause the loss function to fluctuate around the minimum. This is also true. Again, the large learning rate can also cause divergence. A small learning rate always causes the training to progress very quickly. Now this is not true because it makes it very slow, right? So this is false, and the question asks for the incorrect option. So the last option is correct. Alright, so here we have a function given by fxy is equal to x minus 1 square plus y minus 2 square, right? And we are asked to use the gradient descent algorithm, and we have given an initial guess of 0, 0, right? Okay, so let's get started. So before starting with the algorithm, let's recall that in the gradient descent algorithm, how do we update the values based on the previous iteration values as well as the gradient of f, right? So this is how it works. The t plus 1th iteration value of x is nothing but the tth iteration value minus eta times the gradient of f evaluated at the tth iteration, right? So eta is called the learning rate or the learning parameter, right? So what will be the gradient of f? So the gradient of f x comma y will be nothing but 2 times of x minus 1, 2 times of y minus 2. Now we are given that x of 0 is nothing but 0, 0, right? So first we need to compute the gradient of f at the point 0, 0. So gradient of f at x0 is nothing but 2 times minus 1 and 2 times minus 2, which is minus 2 and minus 4. Now we will find x1 by x0 minus, so here eta is given to be 0.1, so I'll write here eta times gradient of f x0, this will be minus 0.1 times the gradient of f evaluated at x0, which is minus 2 minus 4. So the point is nothing but 0.2, 0.4. Now let us perform the second iteration. But before performing the second iteration, we need to compute the gradient at the point x1, which is given by 2 times of negative 0.8 and 2 times of negative 1.6. This evaluates to be minus 1.6 and minus 3.2. So x2 is nothing but x1 minus eta times the gradient of f evaluated at x1. This is nothing but 0.2, 0.4 minus 0.1 times of minus 1.6 minus 3.2. Now this is nothing but, now if we do this calculation here, we will get 0.36 and 0.72. So this is our x2, right? Now we need to evaluate the function at x1 and at x2. So at x1 it would be 0.8 square plus 1.6 square. This will be 3.2. And f of x2 will be 0.64 squared plus 2 minus 0.72, so 2 minus 0.72 square, which is equal to 2.048. Now the question asks for the difference the absolute difference between fx1 and fx2, right? So that will be nothing but modulus of 3.2 minus 2.048, which is equal to 1.152. So the answer is 1.152. So here we have a question where the values of function and its derivatives are given, and we are asked to find the approximate value at a particular point, right? So before doing this, let me recall that if I want to approximate any function value, say f at say x plus h, where h is a relatively small value, then it can be approximated as fx plus h times of f prime x plus h square by 2 factorial times f double prime x, and so on till h to the power n by n factorial fnx. So fnx denotes the nth derivative of x, right? Again, this is an approximation, right? So here we have values of the functions first derivative and second derivative. So we will do a second order approximation, right? So we can say, so, and we are given that the value of the function at the point 25 is 5, the derivative at 25 is 0.1, and the double derivative at 25 is negative 0.002. Now we need to find the function value at 25.1, right? So f of 25.1 can be written as 25 plus 0.1, right? Which is nothing but f of 25, or I should say it is approximated as f of 25 plus 0.1 times 0.1 plus 0.1 whole square by 2 times negative 0.002. Now that is nothing but 5 plus 0.01 minus 0.0002. It should be 0002 divided by 2. So this should be close to 5.010. So the answer is 5.010.
So here we have a matrix, and the question asks if it is Hermitian, diagonalizable, and what can we say about its eigenvalues, right? So let's get started. First of all, it's easy to observe that it's Hermitian. Why? Because the diagonal elements are all real numbers. So diagonal entries are real, and we can observe that the other terms, so for any aij, right, aij is nothing but the conjugate of aji, right? So you can observe that 1 minus I is the conjugate of 1 plus I, uh, minus 2i is the conjugate of 2i, 9 is the conjugate of 9 because every real number is a conjugate of itself. Then 7 plus I is a conjugate of 7 minus I, and so on, right? And the diagonal entries are 1, 3, 5 and 7, right? And all of them are real numbers. So by these two, so these two characterize a Hermitian matrix, and we can say, so we can say that A will be a Hermitian matrix. So A is Hermitian, right? Now what does that mean? That just means that A star is equal to A, right? Where A star means you're taking the transpose and then the complex conjugate, or the complex conjugate and then the transpose. It doesn't matter. Okay, so also A star can sometimes be represented as A theta or as A conjugate transpose, right? So these are also alternate notations. Now let's see if it's diagonalizable. To see that it is diagonalizable, uh, I need to mention that all Hermitian matrices, all Hermitian matrices are diagonalizable, right? Now, why is this the case? This is actually quite easy to see, and this follows from a very popular theorem known as the Schur theorem, the Schur's triangulation theorem. Now, what does the Schur's triangulation theorem say? It says that you take any complex matrix which is n by n, right? Then you can write that complex matrix as u times t times u star, okay? Where what is u? U is a unitary matrix, right? U is a unitary matrix. Now, what do you mean by a unitary matrix? Unitary matrix means you have u star times u will be equal to I. Okay, so this is the idea of a unitary matrix. Okay, now this is the Schur triangulation theorem. Now from this we can see why Hermitian matrices are all diagonalizable. Okay, how do we see that? Now Let us take a Hermitian matrix A, right? Let A be Hermitian, right? What does that mean? That means A star is same as A, right? Now, uh, now by Sharp triangulation theorem, we can write A to be U times T times U star. Okay, I forgot to mention that T here is an upper triangular matrix. Okay, so T is upper triangular. Okay, it's an upper triangular matrix. Now, since A can be represented in this way, and you can represent A star to be U star U star star, which is again just U, right? So this will be U times T times U star, right? And since it is Hermitian, it means A is equal to A star. That means these two entries are the same, right? This will be T star. Now, this essentially means that T is equal to T star, right? Because we can multiply U star and U on the left and right appropriately to get an identity. So T is equal to T star. Now that means, so if T is the same as T star and we also know that T is triangular, that means that T is a diagonal matrix where, and T is also Hermitian. T is diagonal, T is Hermitian, right? Okay. So since T is a diagonal matrix, we can say that A is diagonalizable, right? So essentially A is Hermitian and A is also diagonalizable. Now what can we say about the eigenvalues of the Hermitian matrix, right? What can we say about the eigenvalues of any Hermitian matrix? So let me again write down a result. Let me say that all for all let A be any Hermitian matrix, okay, Hermitian matrix, then all its eigenvalues are real. All eigenvalues of A are real. So that means that we cannot have a non-real or a complex eigenvalue for a Hermitian matrix. Okay. Now, why is this the case? The proof goes like this. In fact, uh, so suppose I take lambda to be an eigenvalue, right? But what does that mean? For lambda to be an eigenvalue, it means A times V is equal to lambda times V, right? Where V is a vector, right? You can say it's in Cn, and also V is a non-zero vector, right? V cannot be the zero vector, okay? So we can say AV is equal to lambda V, right? And what is lambda? Lambda is a complex number, right? It's a scalar. Now, let me take a complex conjugate transpose both sides. So I will have V star A, V star A star is same as lambda conjugate times V star, right? Now what I will do, I will multiply on the right by V. That will give me V star. Instead of A star, I can again write A because A star is same as A because A is Hermitian. This will be equal to lambda bar, which is again lambda conjugate, times V star times V. Now, now we will use the fact that since lambda is an eigenvalue of A, this can be written as V star times lambda V equals to lambda conjugate V star V. Now that is same as saying lambda times V star V is same as lambda conjugate V star V, but this implies that lambda is same as lambda conjugate. So in a complex number, if you have a complex number which is same as its conjugate, that essentially means that this lambda is a real number. So we've seen why uh, all eigenvalues of Hermitian matrices are real, and since this is true, the last one cannot be true, right? So essentially we have seen all of them. In fact, there is another way to look at it. In the Schur's triangulation theorem, What we can say additionally about U and T are that U contains the eigenvectors of A as its columns, right? And uh, T contains the eigenvalues in the diagonal entries, right? In the diagonal entries. Now this is the general case, right? Now we can say we already showed that T is also diagonal and Hermitian, which means the diagonal entries of T is also real. Now that is another way to see that all eigenvalues are real. So this question is a continuation of the previous question. So after obtaining the matrix A, the question says to determine if it is positive definite or negative definite, right? So before uh, going across how to do it, let's discuss a general case, right? So suppose in general we have, so in general, let's say we have a matrix A which is of the form A11, A12, A13 and so on up to A1n, and then the second row can be represented as A21, A22, A23 and so on up to A2n. This goes on until the last row AN1, AN2, AN3 and so on up to ANN, right? So now in the general case we are taking A to be a matrix of the form n cross n, right? So the question is how to determine if it is a positive semi-definite matrix or a positive definite matrix or a negative definite matrix, right? So let me write it as PD or ND, right? So step, so there are several steps. So step one is that you have to look at the leading diagonal entry, right? A11, right? So also let's first discuss how to determine if this is positive definite, and then we will discuss the case of negative definiteness. So for positive definite, so these are the conditions. Condition number one is that A11 should be positive. The second condition is that if you look at the leading determinant, right, which is this particular matrix, this is a 2 by 2 matrix, right? So this matrix, the determinant of that matrix should be positive, right? So we can say that determinant of A11, A12, A21, A22, this should be positive. Similarly, you look at any leading cofactor. So this is called a leading cofactor, right? So for example, what is the uh, fourth leading cofactor? So what is the fourth leading cofactor? The fourth leading cofactor would be A11, A12, A13, A14, and then A21, A22 up to A24, and so on up to A41, A42 up to A44, right? So this is the fourth leading cofactor, right? So you must have got the pattern. In general, you can define the rth leading cofactor, right? So the condition is that all leading cofactors must have a positive determinant, right? All leading cofactors must have a positive determinant. So these are the two conditions to determine if a particular matrix is positive definite. And similarly, what is the condition for negative definiteness? So in case of a negative definite matrix, the way to identify it is as follows. A11 uh, has to be negative, right? And all odd leading cofactors, right? So you can say the third leading cofactor, the fifth leading cofactor, the seventh leading cofactor, and so on. So all odd cofactors, right? Again, leading cofactors. So they have a negative determinant, and all even cofactors have a positive determinant. So this is the condition for negative definiteness, right? Now, since we know this theory, let's try to examine the given question, right? So in the question, we can observe that the first element is negative of 1, right? So this is negative of 1. So we can say that A11 is negative, right? Now, what is the determinant of the second leading cofactor? It will be nothing but minus 1, 1, 1, and then minus 5, which is equal to 5 minus 1, which is 4, right? Okay, so this is positive. And what is the determinant of the third leading cofactor? So the determinant of the third leading cofactor is nothing but the determinant of A, right? Which is nothing but minus 1, 1, 0, 1 minus 5, 2, 0, 2, minus 3. So now if I expand using the first row, I will have minus 1 times of 15 minus 4 plus minus 1 times of minus 3 plus 0, right? So this would be nothing but 4 minus 15 plus 3, which is 7 minus 15, which is nothing but negative of 8. So again, this is negative. So we can observe that the odd leading cofactors have determinant negative and the even leading cofactors have determinant positive, right? So this is actually the condition of negative definiteness, ND. So we can say that the given matrix is negative definite. Alright, so here we have a question where the quadratic form is given in the functional form, which is 2x1 x2 plus 4x2 x3 minus x1 square minus 5x2 square minus 3x3 square, right? And we have to find the matrix representation of this quadratic form, right? So to solve these kind of questions, you need to know primarily two important points. So let me write that down. So facts. The first fact is that the coefficient of x1 square, x2 square, and x3 square, right? All of these will occur in the diagonal entry in the matrix, right? So coefficient of x1 square, x2 square, x3 square will appear in the diagonal, right? And the second important fact is that the coefficient of xi xj will be nothing but the sum of aij plus aji. Right? These are the two important facts. These are the only facts which will help you determine what is the matrix A, right? Now we can say that, so since the coefficients of x1 square, x2 square and x3 square will be in the diagonal, the first thing we can say is that the diagonal entries of A will be -1, -5 and -3, right? Now to find out the coefficient of say x1, x2, right? So the coefficient of x1, x2 is 2, right? So that means the element here and the element here must add up to 2, right? So you can say this plus this must be equal to 2. And then it says that x2 x3 ka coefficient is 4, right? So x2 x3, which means the element here and the element here, right, they should add up to 4. And another thing uh, is that the coefficient of x1 x3 is 0, right, which means this entry, right, sorry, let me mark it in green, this entry and this entry should add up to 0, right? So that can be observed uh, in the third matrix, where you have that 2 plus 2 is equal to 4, 1 plus 1 is 2, and 0 plus 0 is 0, right? So this is the correct answer.